Okay, so here we have a thermodynamics problem where we have to do various pressure versus temperature or pressure versus volume plots based on verbal descriptions. So really we're working on interpreting sort of in words what we'd see on these graphs as behaviors. So we start off with a container with a piston that can be locked or unlocked. And currently it's locked in place so it can't move up or down, so we have a fixed volume. And the cylinder doesn't let any of the gas out, so we have a fixed amount of the gas as well. And we start off at room temperature and pressure. We take that cylinder with the piston locked in, and we put it in a hot water bath. And so, as time goes on, we want to see what happens to both the pressure and the temperature, and then draw that on the graph. So, pressure, temperature. These are zero down here. So, from the ideal gas law, we know that PV equals nRT. And so we're keeping everything constant except for pressure and temperature, and we're seeing how, as we change one, the temperature, right, it's in a hot water bath, it affects the pressure. And this graph, if we rearrange it a bit, P equals nR over V, T, right? And this tells us we have a direct proportionality. And so the temperature must increase, because we're going from room temperature to a hot water bath. Right, so we need to do that that way. It tells us the pressure must increase as well, and it's going to be some sort of linear relationship. Right, so it's going to look like that. And right, I've drawn the arrow to indicate that we go from low temperature and pressure to both a higher temperature and a higher pressure. It doesn't matter exactly how you draw the line, but it should be linear, right? This equation is essentially what we're plotting, so it shouldn't be curved at all. And it must show that as temperature increases, pressure also increases. And the arrow has to point the right way. That's part A. Part B. Part B is one of the very, very rare occasions where I disagree with what the AP test has done, because I think they haven't fully specified the question. So the AP test says, we take the cylinder out of the hot water bath. It reaches equilibrium again. That, to me, means that it's now at atmospheric pressure and atmospheric temperature once again. And at this point, we unlock the piston. My conclusion would be that the piston does not move. It started at atmospheric pressure. It ends at atmospheric pressure. The forces must remain balanced, so it just sits there. The AP test claims that the piston will move down because gravity's going to pull the piston down, right? That's the like an F equals ma type thing. But I think that force of gravity is being balanced by the pressure inside already, and so it's not going to move at all. The AP test does give a note that if you say what I said, that it would remain stationary because the pressures on both sides are equal and it returns back to the original pressure, you would get 1 out of the 2 points for saying that with that reasoning. But they want you to conclude that it moves down. But I don't really think that's a complete explanation. If the piston had been locked in place at a lower than atmospheric pressure setting, then it would move down because it would have to compress the gas until the force of gravity is balanced by the force from the gas pressure inside. But I don't think that's what they said, so I'm not really sure that I agree with that one. But we have a couple other ones to do that I think are worth it, which is why I still included the question. So parts C and D are really the same thing that's going on because we have one graph. And so now we have a slightly different axes, pressure and volume instead of pressure and temperature, and we have two descriptions of the motion. So process C is piston is pushed down slowly, right? And I've written part of this. There's more that it says, but I've written down this because those are the keywords to identify what is going on. So the system is at equilibrium. It's reached equilibrium after part B, and now we're going to push the piston down very, very, very slowly. What that is meaning in AP test language, right? Like that's an equals. If you see this sort of thing in a thermodynamics question, what that's really saying is the piston, actually, not the piston, the gas is always in equilibrium. Right? And in this case, equilibrium means T, right? Temperature equilibrium is constant. Right? We're pushing it down so slowly that the molecules can exchange energy with the outside and always sort of reach an equal temperature before we move the piston a little bit more. That means the temperature is constant. And this bit of information is what we need to make the graph correct. So we're pushing it down. That means our volume has to decrease. So we have to start at a high volume and end at a low volume. And we have to make a plot where the temperature is constant. So that's an isothermic graph, which is like a hyperbola or a 1 over x type shape, right? If I plot P equals nRT 1 over V, right? That's what this looks like. This is like a 1 over x type shape because everything here is a constant. So if the volume goes down, the pressure must go up, and it does so with a curve, right? So that's kind of going to be like this. That's pretty bad. I'm going to draw it the other way, I think. Yeah, more like that. So we start, we end, and we go that way, right? So that is part C. Should look kind of like that. Right, and the key, again, identifying that pushed down slowly means that we're in thermal equilibrium. All right, so now we need to do part D. So I'm going to kind of clear all this over here so I can keep the graph. All right, so now part D. We have a different thing that's happening. So we're starting at that same location, somewhat anyway, same location, and now we're going to pull the piston back up very, very, very quickly. And we're doing it so quickly so that no heat is added or removed. Right, so this is sort of like the exact opposite. The first time we did it really, really slowly, so it was always in equilibrium. This time, we're doing it really, really, really quickly, so it never has a chance to exchange any heat at all. And so this keyword describes a specific type of process, which is adiabatic. This is the sort of the weird process, the one we can't really derive from the ideal gas law. So hopefully you just have to remember this shape. So adiabatic curves are like isothermal curves, but they're steeper. So if we start here and we have to follow a same sort of curve, we know we're going to increase the volume, so the pressure has to go down, but it's not going to be going exactly the same path because the adiabatic curve is sort of steeper. So what we're going to do is going to look kind of like that, right? And we're going the other way, so I draw the arrow pointing the other way, right? And so that's it. You can get a fair number of partial points on this if you have the arrows pointing the right way, where if all you do is recognize the volume and pressure changes without knowing the curvature, you get almost all of it. If you have the adiabatic curve like on the opposite side, so like if you have it curving kind of like that, then you can get most of it that way since you still recognize it's curved. But this is the fully right answer, right? You have to recognize the keywords, remember what process that refers to, and then remember what that process looks like on a PV diagram to be able to reproduce the curve. And that's the problem.